If you want to rotate a 2D vector, the only information you need is the angle of rotation theta. You can then rotate about the origin anti-clockwise with the angle. If you want to rotate in 3D, you need to specify two pieces of information. First, the axis you rotate along, and then the angle of rotation. Okay, that's all well and good, but can we generalize the process? For example, what would you need to do for 4D rotations? Or even more weirdly, can we do complex rotations? We can strip it all down to this. There is a vector, which is n-dimensional, and we want to rotate this vector to another vector, also n-dimensional. The problem is how we can describe rotation in a more systematic way. Let's start with real vectors and then move on to complex ones. Let's list the properties of rotation and see how we can realize these properties. The first one is that rotation is a linear transformation. This linearity means two things, which we can verify in the two-dimensional case. Let's demonstrate the first one of these two. The left-hand side of the equation asks us to consider first the sum of v and w, added by the tip-to-tail method, and then rotate it. But by rotating the whole vector triangle setup, we have also demonstrated the right-hand side. The rotated sum of the vectors v and w is also the sum of the rotated vectors, as the triangle stays a triangle after rotation. So that's the first part of the linear property. The second part is concerned with scaling. Essentially, it means that if we first scale the vector by lambda and then rotate it, it is the same as if you first rotate and then scale it by lambda. This means that because of the linearity property, the rotation is a linear transformation and hence can be written as a matrix. So rotating an n-dimensional vector is the same as multiplying by a matrix on the left. The rotation matrix is denoted as R for rotation, and what remains is to find which matrices correspond to rotation. For that, we can see what the second property of rotation tells us. After rotation, we should expect that the lengths and the angles between the vectors to remain unchanged because, well, we just rotate and don't do anything else. Preservation of lengths and angles imply that dot products are also preserved. So, if it is originally v.w, then after rotating both vectors, it becomes rv.rw, and the two dot products should be the same. But in the case of real vectors, we can also write the dot product as the first vector transposed multiplying the second vector. And the right-hand side can be rewritten as v transpose r transpose rw. This means that the dot product is the same as if you have put an extra r transpose r in between. Because this is true for all vectors v and w, the thing in between is the identity matrix because, well, it does nothing to the dot product. If this feels too much of a jump in reasoning, think about the cases where v and w are basis vectors. As an example, we take v and w to be the first basis vector. If we first multiply on the right by w, then it gives us the first column of the matrix R transpose R. If we then multiply it on the left by the first basis vector, then we have the first entry in the first column. What would this entry be? Well, it would be the dot product of v and w because the matrix in between doesn't change the dot product. In this case, the dot product of v and w is 1, so this first entry is 1. So, using this sort of argument, we will be able to find all the entries in the matrix R transpose R. And if you actually go through each pair of basis vectors, you can actually show that entry by entry, this R transpose R is the identity matrix. So this second property boils down to the rotation matrix satisfying this property. The collection of all matrices satisfying this property is denoted as ON. O stands for orthogonal, and N stands for the order of the matrix R. So, in other words, we can say that the second property implies that R is in ON. However, just being orthogonal is not enough because it's not just rotation that preserves lengths and angles. Reflection also does this. The matrix corresponding to reflection will also be in ON. So we need to use another property of rotation, that it doesn't change the orientation. By that, I mean that a reflection changes orientation. Originally, from red to blue, we go counterclockwise, but after reflection, from red to blue, we have to go clockwise. In this case, we say that the reflection changes orientation. On the other hand, rotation does not change orientation. From red to blue, if originally it was counterclockwise, then after rotation, it is still counterclockwise from red to blue. Linear algebra tells us that the determinant of a rotation matrix is positive. And because lengths and angles are preserved, areas are preserved, so the determinant is exactly positive 1. So that's all the properties of the rotation tells us. In particular, if a matrix is already in ON or orthogonal, and in addition has determinant positive 1, then we say it is in SON. S here stands for special, corresponding to the additional requirement that the determinant equals 1. So this is how we rotate real vectors in n dimensions. What if we want to rotate complex vectors? How should we modify these arguments and the corresponding matrix properties? Well, the first property remains unchanged. We denote this complex case with the matrix U instead. The only difference is that now the matrix U and the vector V are both complex. Okay, so let's move on to the second property of rotation. We previously derived R transpose R equals identity by considering the unchanging dot product after rotation. Now, one very important property of real dot products is that if you dot a vector with itself, then by doing the transpose first vector operation, we get a sum of squares of the components. If the vector v is real, then this is larger than or equal to 0. This is why we can think of this as the square of the length of the vector, with the length being real. If we want to keep this interpretation of length in complex vectors, we can actually just modify one thing. Take the complex conjugate of the first vector, because when we do the multiplication, we get the sum of modulus squared, and the positivity property is restored for complex vectors. So for complex vectors, the only modification is just complex conjugating the first vector. In matrix notation, we use dagger to denote a transpose in addition to complex conjugation. In general, for complex vectors, we define the dot product of v and w as v dagger w, where dagger again just means in addition to transpose, we also take the complex conjugate. For real vectors, we have this argument to arrive at R transpose R equals identity. and the argument for complex vectors is almost the same, just with transpose changed to dagger. Just as a reminder of this whole argument, the left side is the original dot product, and for the complex case, we replace transpose with dagger in the dot product. And the right side is the dot product of the rotated vectors, either by R in the real case or U in the complex case. Then, with a slight manipulation of the new dot product, and comparing with the dot product before rotation, as this is true for all vectors v and w, we previously got that R transpose R is the identity, and similarly in the complex case, U dagger U is the identity. Remember that we use the notation ON to include all matrices, with R transpose R being the identity, with O standing for orthogonal. We want to denote the set of all matrices with U dagger U being the identity as UN, with U standing for unitary. So for the second property, we can write it as the matrix U being in UN. Finally, even though there is no notion of orientation in the complex case, we would still want the complex rotation matrices to have determinant 1. And just like in the real case, where we denote SON as the subset of ON with determinant 1, S standing for special, we would also denote SUN as the subset of UN with determinant 1. So, this is how we can generalize the notion of rotation to higher dimensions, or complex numbers. But here's the thing. Looking back at the defining properties of these matrices, these are practically quadratic equations, and for matrices, these are difficult to solve. By solving, I mean writing down a general form of some sort. Luckily, the set of these matrices, whether it is ON, SON, UN, or SUN, forms something called a Lie group, which is dealt with by Lie theory. The theory will help us get closer to a general form of these matrices. If you don't know yet, this is a part of a video series on Lie theory, and this is the second video on orthogonal and unitary matrices. The next video is going to be a high-level overview of the theory, which I promise is going to have more visuals than this one. Anyway, please consider liking, subscribing, sharing, commenting on the video, and I will see you next time.